Yeah, hello, Mr. Paul. Thank you very much for accepting my invitation to the Mentors Talk program. You have a wonderful career path starting from REC Calicut and to the present, where you are now. So it's a wonderful journey, and you are also continuously adding to your credentials along with the experience, and you stuck to your field of specialization, that is mechanical engineering. You did not go away from it. So it is I think it is a highly focused, committed, passionate journey till now. So if you can share your experiences with us, it will be wonderful. Thank you. Welcome, Mr. Paul, and thanks for accepting the invitation.
Well, I'm so glad to be here, and thank you for the invitation. And I would be so glad to share my experience. As a child, I always wanted to be an engineer. I don't know if I knew what engineer was at that time. But anyway, I was always interested in the mechanical things, taking things apart and things like that. So when I got admission to REC Calicut, I was so happy that I could start my engineering career. And as you know, REC was started in 1961. So we were the first batch. So this was a 5-year course. And fortunately, I was able to get the mechanical engineering. There was only 3 courses at the time: mechanical, civil, and electrical. So after the graduation, I wanted to work in an engineering company. But unfortunately, I didn't get any position. And fortunately for me, I got a job as a lecturer in REC. So I was teaching there for 2 years. At the same time, I wanted to come to US for higher studies. So I was applying to various colleges, and fortunately, I got admission to master's in industrial engineering. At the same time, I also got a research scholarship for the duration of my studies. So all I needed was to get the visa and come here. So I came to US for my higher studies. And the research that I had to do was actually simulating a river.
Okay.
It was a small river in Sioux Falls, South Dakota. And it was to be done using a Fortran language. And the idea was to predict oxygen level downstream from Sioux Falls, South Dakota, using the population level and the output of the meat packing plants around that town.
So this is an academic project, or this was part of your job?
It was an academic project.
Okay.
It was funded by the US government. So obviously I didn't know anything about computers at the time. So first semester I had to take courses in Fortran and then continue with research. And I was able to publish that thesis and get my degree, master's in industrial engineering, and then started looking for a job. So my first job was for a company called RTE Corporation. They were making transformers, anywhere from the pole type transformers, the small ones, all the way up to many MVA large transformers. Now my job there was as an industrial engineer. Since I was the only one in the engineering department who had some computer experience, I was assigned to many of the engineering computer projects. So one of the first things I did was a CPM project, which was the critical path management.
Yeah, okay.
And at that time, we were using a GE time sharing computer, which was a mainframe somewhere. And we dial into that machine using a teletype and use punch cards to create the program. So the CPM was used mostly for some building projects, and then assign the resources and things like that. But it was a big experience. It was very beneficial for our engineers to know what the critical path is and what will happen if the critical path got delayed and things like that.
So what was the team size? Did you start from scratch on the critical path?
Yes.
Okay.
We had to load all the tasks and resources and duration and all those things using punch cards.
Yeah, okay.
And then you get the printout. Then you look at the printout for I think at that time, using the teletype, they will give you a sort of a bar graph.
Okay.
That shows you the duration and then highlight the critical path. But compared to what you can do now, it is very rudimentary.
Okay.
And then I realized that in the time sharing, there are many opportunities for us to do various computerizations. Now, in the transformer manufacturing, they were using an installation called press site. It comes as a sheet, 40 by 48, and then we slit it into various sizes based on the production requirement at the time. In that process, we had a lot of waste. And press site at the time was more expensive than steel because of the insulation characteristics of it. So I thought we could optimize it using linear programming. So we did some experimenting with it and finally realized, yes, indeed, we could optimize it. So I wrote a Fortran program to take the production order for a week and then convert it into an input form that can be fed into the time-sharing computer. And then it'll spit out various combinations of part numbers that can be used to minimize the scrap for that week. So I wrote another program to convert the output into a readable format so the guy on the shop floor can understand which part has to be made and then which combination to use and and so on. So that was quite a successful project for me. And also coming out of college, that was one of my first projects. Then another project that we used linear programming was for the shipping of transformers. At that time, we had customers all over USA and Canada. And we are shipping transformers to all these places from 2 manufacturing places in US and also 19 intermediate warehouses. And a lot of customers insist that they have to have a warehouse nearby. In fact, they will insist that warehouse should be within a couple of hours of their normal operation. Because if there is a disaster, they cannot wait 24 hours to get a transformer. So the project was to minimize the cost of shipping. At that time, there was various shipping tariffs in various locations. So the first job was to get the tariffs in various locations in the US. So we employed a consulting company to create all the tariffs. And then using the tariffs, we created a distribution model. So once the model is created, we could play with it and see what configuration of warehouses and what kind of shipping is optimum for our operation, which will basically be the minimum cost solution for the shipping of transformers for 1 year. So we did a lot of trials with it and finally came to the conclusion that it is better for us to build a warehouse in our main manufacturing facility. So we did build an automated warehouse, and then we started shipping from there. So that also was a big success in using the optimization of the optimization techniques. Now, we were a small company owned by 2 individuals at the time. So at that time, they were getting old and ready to retire. So they sold the company to a much larger company called Cooper Industries. And I didn't like the management style at the time. So I started looking and got a job in Eaton Corporation.
So what was the, sorry to interrupt. So how many years did you spend in this company?
About 10 years.
Ah, okay. That is a long innings.
Correct.
Yeah, okay.
Yeah,
Great.
I didn't want to change the job,
Okay.
but for the fact that the drastic management change. And so fortunately, I got a job in Eaton Corporation. And they were making, excuse me, they were making submarine controls. In fact, they were making controls for a Seawolf class submarine, which was a highly classified project. So at that time, I was an immigrant. So my boss told me, if you cannot get security clearance, we cannot keep you here.
Okay.
So I did, and to get a security clearance, I had to become a citizen. So I became a citizen, got the clearance, then I could work there. And this company was quite interesting that everything was computerized. You know, the purchase order was computerized. And if you don't have a purchase order, you cannot receive material in the receiving dock. Then the shop floor operations were computerized. That means every production order is printed with a barcode.
So this is 70s, early 70s.
No, 80s.
80s, okay. Yep.
Yeah. So barcodes were in the initial stages. So we had barcode readers and, you know, so on at the time. So every operation in every part number is barcoded. So when the operator gets a part or a bunch of parts, he will first use his badge, barcode his badge, so the system knows who the operator is. Then you click on the operation or part number, then the operation number, and so on. And this was all in real time. At that time, we were using digital equipment, VAX computers, and basic programming language. Now, it was so real time that if there is a part revision, we can find out which operation that part is going through, and we can stop it. Okay. So we could say, okay, now use this revised drawing from that operation on, or pull the part back, so before wasting a lot of time on it. It was, and also another thing, the Navy wanted to do us the design in 3D. So at that time, again, everything was done in 2D. And once we installed the 3D systems, then the Navy said, instead of doing the crash testing of the controls, which used to be where you will mount it on a pedestal and use a wrecking ball to hit it. And then we will take pictures and send it to Navy. Well, they said, we don't want to do that anymore. We want you to simulate the crash testing on the computer. So we hired some structural engineers to simulate the crashing. Basically, they wanted to see what will happen if a torpedo hits the controls. So we had to simulate the crash testing on the computer using 3D, then using the color graph, send it to Navy to convince them. And at that time, we were using PERT project management for these operations. And everything was attached to our MRP system at the time. So the managers can not only the critical path, they can also get the cost at the time. So cost incurred, everything was real time. And so that was a good situation then. Unfortunately, the Navy said, we don't have anybody to attack anymore. So instead of 11 submarines, we only need 1. So there was a huge layoff. Needless to say, I got into the layoff and I had to look for another job. And that's when I moved to a company called Metso Paper. Metso Paper actually was a Finland-based company, and they were making paper mills, large machines that make paper from the pulp to the finished paper. Obviously, there was a different type of paper, like the tissue paper, printing paper, cardboard, and things like that. So, and we had the headquarters was in Finland, and we had 7 operations in North America. Fortunately, they had standardized on a CAD system for all our operations worldwide. That was an IBM CAD system, or basically it was a Dassault System CAD system called CATIA, distributed at the time by IBM in North America. The company that I joined, or the division that I joined, was using 2D at the time, CATIA 2D. So when I was given a mandate to convert the 2D to 3D. So fortunately, I was given complete freedom and management support both from Finland and the US. So I created a operation schedule, which included the first thing in that operation was to standardize procedures. And I analyzed the operation in all 7 divisions. I found out that each division was doing whatever they wanted. For example, the title block on a drawing was not standardized. The operation of creating the typing of the description of the part, everything was whatever the division wanted. It's only natural because we acquired these divisions at various times, and nobody took the effort to standardize it. So my first job was to standardize things. That included the drawing operation, the procedures they used to design, and then also the training of the CAD. So one of the first things I noticed is that description of the part was whatever the designer wanted. For example, a bracket was named many different ways. BRKT, BRCKT, and so on. So there is no way to search for a designer for a bracket. So every time you create a new bracket, which obviously costs a lot of money. So the first thing I did was I go into the MRP systems of various divisions and downloaded all the descriptions of the part from their bill of materials. So then I collected all of these descriptions and then sorted it and then threw away duplicates and also all the nonsense names, which I found quite a few, and then standardized into a corporate dictionary of words, and then gave that dictionary to all the divisions, and then told them that only the words in the description can be used as a part description. Now, obviously, it's very hard to enforce it. So one of the things we did in our 3D implementation was to create a menu. So when the engineer starts to create a part or a drawing, you go to the menu and say, start part. And then comes a form that he fills. And one of the field in that form is the description of the part. So when you type each word, it will check against the dictionary. And if it is not in the dictionary, he cannot use it. And the dictionary was kept in a central server in North America. So everybody in all North American locations was using the same dictionary. And only few people are authorized to change it. So you cannot just add a word in it without the authorization of this team.
I'm sure that you would have faced a lot of resistance to bring in this new system. So how did you counter it?
Yeah, it was there, but one of the things I did was I formed like a team or CAD team, which included the designers. Okay. So I bounced it off any idea that I want to implement in the CAD system. I bounce it off against them. Once they approve, the resistance was much less. And then secondly, when anything to reduce their work was a good thing. For example, in this case, when they type it, they don't have to check anything, and a lot of things in the form are automatically filled, like the person's name or initials, the date, and part number, which you'll get it from the next part number in a file or in a directory. So a lot of things are automated that the engineers don't have to worry about it.
So was it a distributed team? You were all collocated, or was it a distributed team?
Yeah, it was mostly from the divisions in the local area.
Okay.
So there was not much traveling because 2 of our divisions were in Canada, and then 2 of our divisions in the New York area. So it was difficult to get everybody together for a meeting. Okay. There was no Zoom meeting or anything like that at the time. But it was successful because I was part of the major division in Wisconsin. So we started doing these kind of standardization. And other thing that we did was we found the title box and the drawing format were all quite non-standard. So we also implemented that. We created a standardized format, through the A, B, C, D, E sizes of the drawing, and distributed that to all of the divisions. And then we are allowed for them to put their title in the title block. Title means the company name, location, and things like that of that division. But the filling of the title block was completely automated. Because when you create a part, now, before I explain that, let me give you a difference between 2D design practice and 3D design practice. In the 2D, you draw a line, and then you call it, this is 2-inch long. Whereas in 3D, you don't draw any lines, you create objects. Okay, so the other difference is that in 3D, you design everything full size. In other words, if you create a plane, or a small bolt. Both are designed as full size, but you can scale it down in the view, and you can zoom in and out to see the whole plane. But everything is designed full size. The advantage is the drawings are created as a byproduct. You can tell the computer to give me a front view of the plane, and then it'll ask you what scale you want it. So you'll say, okay, 1 in 100. It'll create a view of that size. And then you can say, give me a side view or a front view or whatever, or even a cross-section view of that plane. So all of these are byproducts. And because they are designed full size, dimensions are automatic. If you click on two edges and you say where you want it, it'll automatically dimension that part because it is designed full size. So we could actually say, okay, these are the standard views created automatic for any part. Now, the other thing in 3D is that you create a part as an object, but when you want to assemble it, you assemble it as an assembly using constraints. For example, if you want to create a bolt and a part with a hole, you want to put the bolt in it, you can say, put the bolt in it and align the center lines of the hole and the part. Now, the advantage of that is when the hole moves, the part moves, because the center lines are constrained. So if the hole moves, the part moves. Now, when the part moves, the drawing changes and the dimension changes. All of these are automatic. You don't have to do any manual at all. In fact, you don't do anything on the drawing. You create, all the changes are done in the 3D part. Then also, as I said before, we automated the process of filling the title block. And that's where most of the mistakes can be made. So again, when the part was created, we had a description. So the description was transferred to the title block. The date the computer knows, the person's name or initial we know, and we know the weight, because in 3D, you assign a material to the part, and then the system calculates the weight automatic. So you can weight, you can put. So pretty much everything in the title block is automated. And then the next thing that this company wanted was, or they were doing, they were releasing the drawing. When the part is ready to be manufactured, they release the drawing so that manufacturing can make it. Now, one of the things they used to do was they would revise the drawing many times. But every time you revise the drawing, there is a chance they could be making with the wrong revision. So this company has implemented that every part will be started, the operation will be started with a new drawing every time. So there are printers in the shop floor, printing machines, and they will go to the thing, type the part number and get the drawing each time. So even if you make a revision in the last 10 minutes, the new drawing will be there on the shop floor. So there is no mistakes are made there. The other 3D advantage, of course, is you can do a lot of manipulations. The company that I was involved, or the division that I was involved was making a rebuild of the paper machines. They were not making new machines. So in the rebuild operation, we are pretty much making only prototypes. We're only making one machine of an existing machine or replacement of one part of that machine. So we cannot afford to make a mistake. So we have to simulate it. So in 3D, you can simulate the operation. See if it has any touching anything else, any crash, any interference. So all of those we can simulate before we release even a drawing. So that reduced a lot of revisions and also a lot of headache at the shop floor and also at the installation time. The other thing about 3D, the paper machine is that this is a huge paper mill, the size of a block, and they don't stop the machine at all, most of the time. So if you want to replace one part of the machine, they will schedule the operation many months ahead of time. And they will give you a window of maybe 2 weeks to remove the old machine and put a new machine in. So we don't have any time to slack. So we will simulate how the part will be installed and create a 3D movie and give it to the installation people. So they know how each part is lifted by the crane. Sometimes they have to be turned around and inserted in and all that. All of that is simulated ahead of time. So they can minimize the time for installation. The release process was, first we create a TIFF file of the drawing. So it is very TIFF compressed drawing. And then you cannot make any changes in it. And that it is released to a central server. Then later on, we installed a system called a PDM system. That stands for Product Data Management. And that pretty much sits between the design system and the MRP system. So once the design is done, then the designer the design is checked and so on, verified. The drawing is released. And that process also was automated. So when you click on the release button, the system captures all the information, all the metadata about that part from the title block. It reads all those information and create a metadata file and a TIFF file of the drawing and release it to the system, to the MRP, to the release.
Okay.
Yeah, and as it sits between the design and the MRP can access it when a production order is ready, because the bill of material also is in the system. And when this system was installed worldwide, what they did was they had one server in North America, one server in Europe that contained the metadata only. So if I want to search for a part, you go to the search field, select a part, and you can type the description or say bracket, and then see if there is any part that satisfied that in the description. Now, once you find the part, then you can say, get me the drawing. The drawing is kept as a TIFF file on a server in North America, so they could retrieve it within maybe 5 seconds. And that was deployed worldwide. So that what happened was, instead of creating new parts, everybody will search the system to see an existing part can be used. Once they find a part, they can reuse it as is, or they can modify it with a new revision number or a new part number. This saved us tremendously, because there was no use to recreate a part. And when you recreate a part, it has to have all these drawings, all the NC tapes and operations and so on and so forth. Whereas you can reuse a part, drawing is already there, release it to the production and save a lot of time like that. So this PDM system, again, was a very good system where both MRP and the CAD can access it, and then it sits in the middle. And I'm sure there are quite a few systems like that available these days. This was from a company called matrix data. So again, many years back. So these are pretty much my experience, which can be summarized into the integration of engineering and production, and quite a few optimization systems in the beginning of my career. So, I was happy with what I did. The last job I did with the Mezzo paper was the most satisfactory job, because I had full support from the management from Finland and management from North America. And they also give me pretty much freedom to do what is necessary. So the resistance, as you asked before, the resistance was less because of the management support. All they had to do was write a memo and say, this is the way it's going to be. And so they know I have the support. And then they know they have the support of the designers. So I didn't feel there was much of a resistance, but there are some, of course, because especially since we are going into divisions in Canada and so on, So they had their own, nobody likes to change, their own method of operation. So first thing you had to do was get the support of their management. And then make sure you give the training so that they know what to do. So, there are ways to overcome the resistance. But I'll be the last one to say there was no resistance. There was resistance, but you have to overcome, because standardization, makes a lot of sense. And, maybe you'll have to convince them the reason why you have to do this. Because, for example, the standardization of the drawings. We are one company in North America, in the world, but the customer gets 3 drawings and they look 3 different ways. So they will ask the question, you said you are one company and you have 3 drawings that look different. So, there are obvious reasons. All right?
Yeah, that's great. Okay, that is a suspense thriller kind of professional life of a mechanical engineer. The most interesting thing is it's all diverse industries.
Mm-hmm. Yes.
Okay, so initially it was, I think, if I'm right, it was production planning and control, MRP systems, then scheduling, then moving on to defense-related projects.
Right.
Then getting into paper industry. So, and there it was more of 3D modeling and stuff like that. So one path you would have updated your technical knowledge about these things, and on parallelly, I'm sure that you would have updated your the business knowledge also, because it's all diverse industries. So you would have spent a lot of time in studying things. So, and plus, when I went through your profile, I saw a stint as a visiting faculty in one university also.
Yes, the reason was when we were going to 3D, we found out in the local area there was a shortage of 3D designers. So we started thinking, how can we solve this issue? We cannot hire a 3D guy. There are a number of other companies also using the same CAD system. In fact, 80% of the aeronautics companies and 60% of the automotive companies use this IBM CAD system. So what we approached the technical college and asked them if they can offer a CATIA 3D design course in the diploma course. So they said, we can do it, but we don't have any instructors. So I volunteered that I will do the instructing. So for 3-4 years, I did that. And in the process, we created a lot of engineers or people with CATIA 3D experience or knowledge. So we could hire those kids in various industries in that area.
And another interesting factor is, see now, these managements always entrusted you with key projects. And I'm sure that they would have trusted you very well. Otherwise, they would not have delegated those things to you. What is the, what was so special about you, for them to trust you so much?
Well, the one thing that I had in my, in my resume, that I had a mechanical engineering degree. I had a master's in industrial engineering. I also had an MBA in finance, which I acquired while I was working. So I had some credentials to start with, but I also had various experiences. And then fortunately, I had some trusted managers. For example, when I was doing the optimization projects, the company went through some bad times and they had to lay me off. But my manager said, don't worry, you can continue the project from your apartment. I will install a computer terminal in your apartment. So I had a teletype machine in my apartment to access the time sharing through the telephone and continue the project. So once I get the preliminary data, he showed it to the management and he said, oh, we have to hire him back.
Yeah, okay.
So there are some key people who supported me. And that again, I guess it could be my knowledge level at the time, or it could be just pure luck, or whatever it is. I was fortunate to be able to accomplish these things.
Plus, your career path, it never had a very short stint, short stint with any company, because everything was a minimum of 5+ years.
Correct.
So I think they would have got a feel that this guy is pretty serious and committed, because he doesn't have any patch of less than 5 years.
Yeah. I think each item or each job, I go in as this is my job. I'm going to retire from here. But due to circumstances, I had to leave. First job because of a takeover by another company. Second job because of the Navy canceling. And then the third job also, I worked there for 14 years and enjoyed every minute of it.
Yeah, so I think every setback was for a better one.
Correct, yeah.
Whenever he lost his job, he got into a better position. Otherwise, he would have continued there.
That is correct, yeah. Yeah.
And go ahead, please.
Yeah, it was very good. After I left the last company, I started consulting for the same company as well as for another company called Komatsu Forest. This Komatsu was making an interesting machine. Again, they wanted to install in 3D and the PDM system. So their product was tree cutting machine. This is a machine that is mounted on a tractor. It comes and hugs the tree, cuts it, and then tilts it, then cut all the limbs off, then chops it into sizes. And they even use an algorithm in the computer on the cutting machine that, depending on the taper of the machine, it calculates the length to cut it. So if it is a big taper, they'll cut it short. If it is a slow taper, then cut it longer. And that was all done in 3D after I started consulting with them.
Okay, so I think that was a very long career as well as maybe a very long interview as well. Thank you very much for sharing your experiences with us. And I'm sure that this will give a lot of value to the fresh engineers, or especially mechanical engineers who are getting into the profession or the career path. One interesting thing was you were always on projects. Yeah, so it was a combination of mechanical engineering and small or large projects was spanning your entire career. Your MBA degree also helped you, business knowledge helped you, continuous technical upgradation helped you. So when I interview people, I see these patterns actually. See, they had excellent academic backgrounds. Okay, so nobody became an engineer by accident. They wanted to be an engineer, so they became an engineer. And you are also not an exception. You said from childhood onwards, I wanted to be an engineer. And then you struck to that engineering path. You did not deviate from it. And continuously you are studying and upgrading your knowledge, both on the managerial side as well as on the engineering side. So the patterns are very common whenever I interview successful people. The patterns are very clear, and your profile also matches the trends which I could infer. Thank you very much for your time. Yeah, that's it. Thank you.
Well, thank you, Rajan, for this time to share my experience. I hope somebody can learn from this experience, and I'll be more than happy to help you or help anybody else whom can use some of my experience. Thank you again.
Thank you. Thanks.